I hope you're in a good mood. I will sing a little song for you tonight, today, not tonight. I hope you want to improve the performance of your application, because that's what I am really into it. And please follow my talk, which is called Cut My Task into Pieces. This is Concurrent Mode. Oh, thank you. Thank you, thank you. So, what happens when a user interacts with the application? Do you know? The browser will create a task and tries to execute the code you have written. In this case, we have a click listener. It will execute some work, and it will execute also some other work. And in the end, you see a little bit of painting and a little bit of style recalculation. This is what usually happens. This is a normal task, how it looks usually. So let's break it down a little bit. You have, like, on the very top row, in the dark yellow color, you see what the browser does. So this is the browser event, always. It can be XML HTTP requests. In this case, it's just a click listener. It can be also drag, input, or whatever other DOM API you are just like hooking into and try to execute code on that. On the bottom side, in this light blue color, you see that your application code is running. It can also be like third-party code, for example, some one password or LastPass that is like putting images into your input boxes if you want to sign in. But generally speaking, this is like your application code. So in this case, work and other work. And then the end, rendering and paint. On top of just normal tasks, you also have long tasks. Long tasks are typically shifted in red, and they indicate like there's work executed that takes longer than 50 milliseconds for your client to actually calculate it. So what the blocking time here is 14.9 milliseconds in this case. Like, the blocking time will be always be shifted in red, and it will indicate you how much time you spend over the threshold of 50 milliseconds. So in this case, we have around 15 milliseconds blocking time. It looks scary, right? Because it's red, it has a triangle, everything is scary with the red triangle. So why should you actually care about that? Well, there is this new beautiful INP metric which replaced FID in March 2024. So this is like very recent change to the new core web vitals. And I think Michael already introduced you to a little bit to INP. And you only have 200 milliseconds of time to actually get a good score. So any interaction a user does, you have 200 milliseconds of time to calculate it on the client's computer. So you have to take care of how performant is your code actually on the client. So let's break it down a little bit. INP has 3 phases. You have the input delay, which should be, in best case, 0. So this is the time that takes the browser to, like, it receives an input, you want to click somewhere, and then the time until it can actually execute the code, this will be your input delay. Usually should be 0. Then you have processing time. Processing time this is the code you are executing. So you have a click listener, then you do some stuff, logging to database, informing some other clients. That's what the processing time is, like what the CPU of the client's browser has to execute right now. And in the end, you have presentation delay. This is like how long it takes for the browser to actually like render the new change and present the new frame. And all of it together will be your whole INP metric. And you have only 200 milliseconds time for that. So let me quickly introduce myself. I'm Julian Jandl. I'm a performance engineer, as I like to call myself. And I'm working for the company of Push-Based, which Michael said he likes it. I also like that. It's a nice company. I'm trainer and consultant there. I'm also doing some improvements. And I'm also RX Angular core maintainer. This is very important for this talk. So let's go into a little live demo here and take a look at what INP is, how you can see it. And I will just switch to my browser here, and I have prepared a little demo application. This is working good. Just a little delay, but yeah, it's good. So I'm right now at the blank page here. So everything is blank. What I want to show you is how does it look if I just go here to this. Click this. Back. What happens if I just click on this native route? First of all, I have installed a browser extension that will give me information about Web Vitals. So I can just click here, and then you see here 360 milliseconds already in orange needs improvement. My laptop is right now charging, it runs at full power, and it's it's a recent one, so it has decent performance. Let's see how it's looking when I slow it down and I throttle my CPU a little bit. That's more like a mobile device now. And now you should see like 4 seconds. This one here is 1 second. It took me 1 second to just render the next page. 1 second is red because it's 5 times 200, and that's not a good thing. You can also see here in this, because of this browser extension, how it breaks down. So you get information about input delay, you get information about presentation delay, and you also get information about how long your script took. So let's break it down a little bit and see the flame charts. So what I can do here now is just press the recorder button, do the navigation again, stop the profiling, and now we see here this very long task. You see like this red shifted area, it says 929 milliseconds, and it says animation frame called. And here in this interaction pane, I can see the interaction that happened. And this small box here on the very left side, this is the actual interaction code. This is the pointer. It's just a click event. Then we have an animation frame scheduled to render our changes. But all of this adds up because in the middle of this process, no new frame could be presented. And that's what you can see here from the candle. So at the very end here, at the right side of the candle, you see this is where INP gets its end event. And everything that happens in between, until the browser can generate a new frame, will be accounting for your INP metric. So this is how very bad INP looks like. Wrong direction. So what options do we have? We have now this 1 second long task. What can we do about it? And we also have a very bad INP measurement. We can be super smart and we just schedule that thing away, because then we have a beautiful, nice INP measurement and just everything of the work is done in the future. No one cares, we have a green metric, everything cool. What options do we have to do that? We can use like set interval, set timeout, a request idle callback. We can also use scheduler.post task. This is a very new API, or the message channel, maybe a little bit unknown, but it's also possible to do that. It works essentially like a timer. We cannot use request animation frame though. We've seen it before, because this will happen before the next paint, and we want to like put work after the next paint. So yeah, this is this is the initial state. We have very bad INP. With improving it by using a scheduling technique, we can just make our pipeline green, like our measurement is green, INP is good. And the whole work is just executed at a later point in time. But no problem. Let's take a look how this is working. So we'll go again to this demo application, and maybe you noticed before, but there is a button that is called scheduled. So what I can do now, just show by the console here, let's clean it, and I will just click on the scheduled now, and you will see like there's no new measurement, no bad INP value, it's just violation set timeout handler took a long time. I can of course just repeat the whole process, and now you see I'm still throttled, by the way, like it's 4 times throttling enabled. 100 milliseconds, before we had a second. So metric is perfect. Let's quickly check the code, what I did here. It's very straightforward and a little bit stupid, but instead of using a router link directive to execute everything immediately, I have just a custom function which is called navigate to native scheduled. And what it does is it essentially just calls a set timeout and then routes after 15 milliseconds. So what can happen before is this ripple effect on the button. That will be counted as a new frame. The browser presented you with a new frame before creating a new page, and you have a good metric. So it works. You get a better metric out of it. But there's a problem with it. What will happen if a user tries to interact with the application again after you click the button, you have 1 second delay because you are executing 1 second of JavaScript work, and you again try to interact with the application in the middle of the process? Well, then you get a very, very long input delay. What I said before, that should be 0. In this case, it cannot be 0 because the browser is right now occupied with doing other work. It cannot do things in parallel because it's JavaScript. JavaScript is single-threaded. So we will get a very high input delay amount here, because when you try to click on the page while the browser is executing stuff, yeah, it cannot do it. So to understand how this works, let's dive a little bit into the event loop of JavaScript. So how does JavaScript actually run in your browser? How is it interpreted? Essentially, there's an endlessly going while loop. It's just waiting for a new task, execute the task. That's it. Super simple. What is this queue? The queue is the macro task queue. What is a macro task? Every DOM API you can think of, like input, click, dragging, everything the user can do with the browser will spawn a new macro task on this queue in the main thread. You can use like every timer, every idle callback, every message channel, also request animation frame, and of course, as I said before, like all the third parties will all end up on this very same frame, very same thread, and they will cause your application to run it there on this one thread you have. So let's take this example here. We have a script evaluation in the very beginning, then we have a mouse down followed by a click, because first mouse down happens, then click happens, and the click spawns a timer fired. And the event loop runs with this run to completion model in the background. So it has to finish its job before it can start a new one. So this is the stack. First we execute work and work 2. So you can see here the task is getting executed, and before it can execute the click event, even though the browser knows already it has to execute it, it cannot do it before. On click we do something on click, of course. That's what we are intended to do. But then we just schedule our work, as we did before, into the future. And this is like huge work. The user tries to interact with our application. We get a new input. Of course, the browser is already aware of it. It puts it onto the stack. It knows that it has to execute it, but it can't, because it is still executing something else. And this is how you can get really high input delay, because your main thread is completely occupied by stuff. So yeah, this is again the full breakdown of INP, how it looks like, and how you can end up in a state where you have high input delay. So let's take a look at how this is actually looking like. Wrong button, I'm sorry. Like this. And then I go back to my application here. And what I will try now is I go to this scheduled route or native, it doesn't matter. And in the meantime, I try to interact again with the application and try to just click. I'm just clicking here right now. Yeah, should get some results here. So all of those were the interactions I did while the browser was actually executing. And what you should see here is, yeah, this one here, a second of input delay, because the browser was just right now executing stuff. Let's take a look at how this is looking in the flame charts, because you can also observe all the interactions in the recording. So I tried to click again in the meantime here. And this is what you see then. This would be here in the interaction pane. This is our good interaction, so the interaction that sends us to the new route. Then here, the candle starts exactly at this point in time here. That's what you can see. The candle starts in the middle of the process, and you can see the candle is going all the way up until here, when you finally can like process what you wanted to process. But everything that happens before is just input delay, because the browser cannot handle it anymore. It's only single-threaded. Very good. So we now know all of the problems. We do too much work. We create long tasks. But what to do with them? Like, how can we solve this issue? My good friend Kirill, who can sadly not attend this conference right now, suggested to play a little game. You know, maybe some of you know this game. Like, was it called Bricks? I think it was called Bricks, where you can just, like, with the ball, kill the tasks. Unfortunately, this is not possible, but it looks fun, so maybe we can play some. What we can actually do is we have 3 options to deal with those long tasks. First of all, and that's the most preferred solution all the time, we can reduce the work that we are doing. This is like super individual task. That is something that you as a developer have to take care of. You need to be aware of the domain. You need to be aware of what is going on, and then be able to improve, for example, algorithms, or go from immutable to mutable, because mutable is like more performant than immutable. Stuff like that. This is typically very hard to achieve. Of course, if there's like something obvious going on in your application you don't want to execute right now, then yeah, just like execute it somewhere else or someone else. But yeah, reducing work is very hard to do. The other options we have is distributing work and prioritizing it. So what we can do is like we take the big chunk of work, chunk it in smaller pieces, and then execute them one by one, bit by bit. Of course, there will be work that is more important than other work, and that's why we also want to be able to prioritize our work. And this is where I need to introduce you to the RX Angular Concurrent Mode. This is what the talk is all about. So we try to port the latter two improvements, distributing and prioritizing, and provide a library to enable you to do that. So, by the way, the name is stolen from React. React already has concurrent mode officially. It's still in experimental mode, but it's official. We try to port what React did to Angular. So there are two concepts, distribution and prioritization. We have three things: scheduling, we already know of, then chunking and frame budget, like control the size of how big should the chunks be for the distribution, and then in the end, we want to prioritize them. So yeah, scheduling, this is the technique we used before. You've seen it before. It can lead to problems, but it can also improve your metric just from the beginning. So this is very straightforward. What we actually want to achieve here with chunking is not schedule it just somewhere in the future and just like still block the main thread. We want to splice up our work into chunks and execute them bit by bit. Because you want your users to be able to react or to interact with your application all the time. That's a no-go that the user tries to click on your application and it's not working at all. This is like the most frustrating experience you can have. So let's take this as an example. You can do it just by the template, for example. Very easy. So we have the header, content, sidebar, footer setup I've shown you before in these beautiful colors, and we have just 4 components rendering them. So what would chunking mean? First of all, on this click listener, we render sidebar, body, header, footer at once, synchronously, directly, on click. What we can do is we can chunk it by the component. So we want to first render header, then sidebar, then body, then footer. Super straightforward. You just import rxlet from Rx Angular template package. Go ahead to your template file and apply the structural directive rxlet. In this case, it's an empty input. Of course, if you want to pass some state, observable state in this case, or a signal, also possible, you can just assign some state. In this case, it's just empty, just for the chunking. We can also do the same thing for lists, because lists are typically the thing that prevent your page from being super fast. Imagine you open up this movie application and you render 1,000 movies at once. They have to be rendered synchronously, no chance to do it otherwise. So everything has to be rendered at once and it's getting slow. So yeah, this is how it would look like. You have this click event listener and then you're rendering item, 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 item. And you want to fix that. So you can just, instead of using ng4, use rx4 in your template. So yeah, it looks like it looked before. Of course, we cannot implement the control flow. This is really sad, but we want to have a discussion with the Angular team maybe, so to open up the standard, so we can also deliver custom structural components. But yeah, you have to deal with this at the moment, so rx4 instead of ng4. And this will do exactly what I told you before. So it will chunk the items, which would be a long task before, and render them bit by bit. But of course, it's not like super dumb and would just take each view and create a new chunk out of it, because this would create way too much overhead. Instead, you have a configuration for it, like how big should be the pieces of work you execute bit by bit. So default configuration would be the configuration in the middle. Is this, by the way, the lighter? Yes. So 60 FPS would be the default configuration, where you have like 16 milliseconds per task. So our algorithm behind the scenes tries to chunk down your task in 60 milliseconds portions and then execute them bit by bit. If it's not possible, it's not possible. But it tries to. So let's take a look at how this is looking like. I'm going back to my demo application here. And you might notice there are more buttons which say concurrent and concurrent prioritize. Let's check out the concurrent one. So I'm still throttled, so, and also there's a little bit delay, so you should be able to just tell by your eyes. I would just click here, and you see header bar was inserted first, then sidebar, then content, then footer. Let's do it again here. The items we wanted to render are chunked now. What we can improve here is, because I told you about lists, and this is a list here, we can use just RX4. So let's go ahead and switch a little bit of the code here. So what I have here in place, I've shown you before in the slides, is the component plus the RxLet directive. What I want to have here is replace ng4 with RX4. So let me quickly refresh this page, and maybe some of you already noticed, but if I just click here on the concurrent now, you see body is inserted immediately, and then the scroll bar is like adding up because all those list items are rendered bit by bit. Let's take a look at the performance recording because this is interesting. So I'm clicking here, and now you see all the list items were added here. So let's take a look at this flame chart. Yeah, so now you can actually see the chunking is happening. So first chunk you see here, 180 milliseconds. Of course, if you can, like, the algorithm cannot improve your chunks. It's impossible. I just told him to please chunk up header, sidebar, footer, whatever, and whatever the length it takes, it will take. So that's why we see 180 milliseconds here per task. But what is very interesting is here on the right side, because this is how it looks like if the list items are rendered. And you can also tell here by the screenshot section that the items are added up. You see the scroll bar is getting smaller and smaller and smaller and smaller. This is because all the items are rendered here. So one task, 11 milliseconds, 12 milliseconds, 11 milliseconds. So this is the algorithm really trying hard to focus on your frame rate that you have configured and then render them bit by bit. Ah, I forgot something very important. It is abortable. So I can here go to the concurrent and immediately go back to some other route. So concurrent, blank, concurrent, blank, concurrent, blank. No problem, because we can abort the work. There's something in flight, we can abort and just skip it entirely. If I try the same trick here with native, won't work at all. Native, blank, delay. And there you see violation set timeout handler 1 second. Screwed up. I don't want to have that. I don't want to be blocked while something is going on. INP 7 seconds. So what we want to have is this abortion. Last thing I want to tell you is the prioritization. What we did now is rendering first header, then sidebar, then body, and in the end, the footer. Apparently, for most people, the body is the most interesting piece of information you want to have, and you also don't want to screw up your LCP measurement, right? So the most important stuff should be rendered first. Right now, it just derives the information from the template. You have first header, then body, and that's why it schedules them one after the other. But what you want to achieve is having the body as first, or index 0 in this case, and move around the task on the queue. You have a set of priorities you can choose from. We didn't number them, we call them by name, and this is also a little bit stolen of the React implementation. They also called them by those names. That's why we also adjusted like that. So it's immediate would be the priority with highest priority. Then you have user blocking, normal, low, and idle. And idle, as you can guess, will be lowest priority of all of them. So what we can do with our current example is just apply lower strategies for the header and the footer and give the body the most important strategy immediate. That's how you can choose the priority when elements enter your screen and what is the most important stuff. So let's go back to the demo application here. So you can see here concurrent mode prioritized, and if I will click here, you will see the content is the first thing that's getting added to the DOM because we said so. I can also show you the code here. So I cannot, because I can probably not open the, yes I can. Ha, so cool. Concurrent priority. There you go. And this is how the end result should look like. So we have strategy low here, we have strategy immediate here for the main content. For the list items, we give yet another strategy. And for the footer bar, this is the low priority. And the end result will be, I click here, click on prioritize, and you see first content, then the sidebar is rendered, then the header, and finally the footer, which we care least about. So yeah, I'm starting wrapping up here. So please make sure to like and check out our GitHub repository, RX Angular. Check out the concurrent mode. Check out this very beautiful article of my good friend Kirill, who writes like a masterpiece about explaining what is INP, how does it work, how can you improve. And there's also some parts we have discussed today in it. Finally, again, I'm Julian Jandl, in case you forgot about it. But I sang for you, so probably you don't forget about me. Also, as Michael suggested before, I like to work for Pushbase. No, I'm really happy about working for Pushbase. It's such a nice company. We do web performance consulting, for example. If you want something like that, please book us. And yeah, grazie per l'attenzione.